Okay. So so today we are going to talk about we are going to cover a little bit about hashing. Hashing has like two lectures, the hashing 1, hashing 2. Okay, but I don't think we can even finish hashing 1. Okay, so yeah. Anyway, so what is hashing? So first, let's consider the symbol table. Okay, what is symbol table? Symbol table is like this. Okay, it holds n records. Okay, so each record looks like this. Okay, so it's like kind of like a database, like which you have a key. Okay, and you have other fields. Okay, that contain, for example, for example, like a student record. Okay, you are a student, and you have like obviously you have name, you have like your student ID, you have like maybe your rank. Okay, you are junior, and maybe like a number of classes that you have taken, things like those. Those will be your satellite data. Okay, but for take student record as an example. Okay, here, okay, the key, okay, would be your ID. Okay, so so this is a symbol table. I mean, a record in the symbol table. So how should such a data structure, okay, be organized? Because like we are going to consider the insert, delete, and search. Okay. So obviously we are going to search or insert, okay, through this key. Okay. So we want to do these operations efficiently. Okay, efficiently. Okay. You could imagine, okay, you could do this thing, okay, through an array. Okay. But how do you arrange an array so that you can do this operation very efficiently? Okay. So suppose that keys are drawn from the set, okay, U, okay, which range from 0 to n minus 1. So it has like a range for these keys. Okay, and the keys are distinct. So different records have to have different keys. So you can set up an array of t from 0 to n minus 1. Okay, such that like tk will hold the this key. Okay, the record x. Okay, with key k. Okay, so the k will be the same as your array index. Okay, so if it's there, then obviously like your record will be will be there. Okay, after the insertion. But if the record is not there, okay, this array location is going to hold nil. Okay, just indicate that there's no record there. Okay, so because once you somehow integrate the idea of key and the index, okay, the operation, okay, of the insert, the delete, and the search, okay, they all take you know, ideally, you know, constant time, right? You know, but the issue, there's an issue there, okay, associated with this approach, because like the range of keys can be very, very large. Okay, suppose you are using the key is like a 64-bit. Okay, represented. The keys are represented by 64 bits. Then, okay, potentially it could hold this many keys. I don't even know how to pronounce this. You know, this is like a, let me see, 1,000, million, billion, trillion, and then beyond that, I don't know how to pronounce that. Okay, but anyway, obviously you can see that there are so many different key possibilities out there. Okay, and if you consider your key to be character strings, such as your name, okay, it could potentially be even larger, because like each character is going to be represented by multiple bits, right? Okay, for example, like your name. Okay, we could potentially use your name as the key. Okay, but it's going to, you know, it's going to be obviously quite a large number of bits, and potentially it's going to be even larger than this number, potentially. Okay. Although I say that, I mean, let's not consider this scenario. Let's just consider your student ID. How many digits are there? Only 5? 5? 9, right? 9. I mean, that's already quite a lot, right? So it's you know, 1,000. So 9 digits, like up to like a billion, right? Billion. But obviously, do we have this many students at NCU? You don't know how many students we have at NCU? I think we have like between 10,000 to, we have less than 20,000 students. Like probably around like 1,000, I mean, maybe less than 15,000, I believe. Yeah, yeah. I mean, if you compare like NCU with like for example, Zhongyuan, I mean, they have like a smaller campus, but they have like more than twice of the number of students. You know, so to be honest, like you know, Zhongyang campus, you know, is pretty nice. You know, if you consider the number of students, you know, but think about that. I'm talking about in the order of you know, tens of thousands, right? Tens of thousands， 就是几万个学生嘛，几万个学生几位数？5位数嘛，对，5位数，好吧。Even if you consider National Central University from the day in China, okay, like in 南京 ，OK， 你知道中央以前哦，最早的时候中央是在南京大学哦，你们知不知道在理论上其实那个就中国第一所大学就是南京大学，所以中央大学 I mean theoretically speaking 也是中国第一所大学，不是北大哦，不是清华哦 ，OK， 不是南京大学 ，OK， 那不过这个都是过去的事情啊，就让你们知道一下。那 anyway，so even if you consider like you know I mean the NCU okay for like 100 years. Okay, remember I just mentioned like each year we only have like at least 5-digit number of students, and if you consider 10 like 100 years, you know you have, you know, at the most this you know let's say 100 million. Okay, that's overkill. 100 million times like 100. It's going to be like in the vicinity of like a trillion, right? A billion. I'm sorry, billion. So that's far below the 9 digits, right? 比9个位数可以那个来存的来储存的这个 record 啊，少太多了，对不对？就算你考虑100年，事实上这个我们知道说，每一年我们进来中央大概只有大概只有3-4千名 ，OK， 大概只有3-4千名，连研究生连大学部 ，OK， 所以事实上应该说3-4千名乘上100啦，应该是用5000来算好了，5000 5,000 times 100， 所以5000 5万50万 ，only like 500,000。Really not too many students, but we have like 9 digits. So, obviously, if you try to create an array with like with index 9 digit long, it's going to be a gigantic array, right? But you can imagine in most most of the index will hold nil. There will be no record whatsoever in that array, right? So to make like your array to be more how should I say, like cost effective, we usually use hash function to deal with that. Okay, so we use a hash function h, which map the universe U of all keys into your array index. Okay, so we have like all these keys, K1, K2, K3, K4, K5. Okay, all these keys. Okay, remember this universe, it could be very, very big. Okay, such as 9 digit for student ID. So the potential universe could be very, very big. But in reality, the number of keys is really not that many. Okay, so this S is the set of the keys that really exist in this universe. So this S actually is a very, very small set, okay, compared with like the size of U. Okay, and this hash function basically help you to map from these keys to your index, to your array index. Okay, so when a record to be inserted maps to an already so supposedly, okay, so you can look at this example, okay. I mean, each record is mapped, okay, to a different location. Each key is mapped to a different location, but there's some issue. First issue, K2, K5, I mean, when the hash function, okay, this sometimes happens, okay, when hash function, okay, map 2 keys, okay, into the same location, okay, we have this HK2 equal to HK5, okay. For the other keys, they are mapped to different locations, which is nice. But the K2 and K5, they happen to be mapped to the same location, okay. So when a record to be inserted, mapped to an already occupied slot in T. So for example, say previously you already insert the record for key K2, and now you want to insert the record for key K5, okay, because this record has already been occupied. This slot has already been occupied by the record with key K2. So obviously, like you cannot do that, right? So there will be a collision. Okay, we say this is a collision. A collision just means like, multiple keys are mapped to the same location. That's what we call collision in hash function. So how do we do? One way to deal with it is that, okay, for each location in the array, instead of storing only one record, you can use a linked list. Okay, you can use a linked list. You know linked list from data structure, right? So you can use a linked list to store multiple records. Okay, in this particular example, you can see the key 49 and the 86, key 86 and key 52, they happen to be mapped to the same index I, and because they are, they are inserted in the order of this record 49, and then this record 86, and then this record 52. So you can see that, okay, this linked list appear to be in this order. So, if we do that, okay, then, we somehow, resolve the collision. Okay, we call such an approach as chaining, as a chaining. In the chaining, as I say, like each position in the array is a linked list. Okay, it's a linked list. Okay, but this approach has a potential for the worst case to happen. What is the worst case? The worst case is that, okay, if all the records happen to be mapped to the same location, again, this is very unlikely, okay. If a hash function has too many collisions, most likely your hash function has some issue, as we will discuss later, okay. But anyway, okay, if that happens, if all the keys, all the records are mapped to the same location, okay, every key are hashed to the same slot. So if that happens, the access time, okay, will be linear to the number of records, because like you need to travel to the end of the linked list to insert one record. Okay. Of course, I mean, because it's a linked list, you could play smart. Okay. For example, the insertion, you could insert it, I mean, here, okay, at the beginning. So, yeah, the insertion can be done in constant time, okay, because you can insert it. I mean, you can the new record can be inserted here. You know how to do that, right? In the linked list, okay. Deletion, but the deletion and the search, you cannot avoid, the possibility of going through every record in the list, right? Because you need to know where to delete, which record to delete, or in the search, in the case of search, you need to find that particular record. I mean, which you don't know where it is, so you have to go through every single record. In the worst case, it may appear, I mean, as the last one. You don't know, okay? So, the time, for the running time for the insertion may still be a constant, but the running time for the deletion or like the search, I mean, has, the worst, of course, in the worst case, I mean, it would be, linear. Okay. So, how about average case? The average case analysis of chaining. Okay. So here we make the assumption of simple uniform. Okay. What is simple uniform? Hashing. Simple uniform hashing. Okay. It's defined to be like every key is equally likely to be hashed to any slot of table T, independent of where other keys are hashed. It turns out that this simple uniform hashing is not that simple. Okay, but let's make such an assumption first. Okay, let's make this assumption first. So if so, let's define one thing first. Let n be the number of keys in the table, and let m be the number of slots, or you can say m is the size of the table. Okay, we can define the load factor of table T to be alpha, which will be n divided by m. This is the average number of keys per slot. The concept is very, very simple. Okay, concept is very, very simple. And once we have this load factor defined, then the expected time for an unsuccessful search for a record with a given key is, 1 plus alpha. Okay, because you need 1 to map to that particular location, and because alpha is the the average length of your linked list, right? So you need traverse the whole list, in order to make sure this is unsuccessful search. Okay, so it's 1 plus alpha. Okay. So this is like a apply hash function. Okay, it takes constant time, and once you calculate, the hash function, the axis of slot is constant time, and then the alpha is the search. Is the time to search the list. Okay, but the expected search time is theta 1 if alpha is like a big O1. Obviously, because according to this formula, obviously, okay, if alpha is like constant, or like at least it's not like it's not big, or equivalently, if n is big O m, because alpha is defined to be like the ratio of these two numbers. Okay. So if n is big O m, so alpha obviously is is constant. Okay. So a successful search has the same asymptotic bound. Okay. Basically, you can assume like it's like a half of this amount of time, right? But still, like it's like 1 plus alpha. Divided by 2 is, in terms of time complexity, is still the same formula. Okay. So it's it will be same asymptotic bound, but a rigorous argument is a little more complicated. Okay, you can check out textbook for like a more rigorous definition. Derivation of a successful search. Okay, time complexity. It will still be like 1 plus alpha. Okay, then it's about how we choose a hash function. As I said, okay, a good hash function should have the property of simple uniform hashing. Okay, but it's hard to guarantee. But I think I'm running out of time today. Because choosing a hash function, it takes some time to finish. I think I will stop here today. Okay, because after all, this part will not be covered by the midterm. Okay, including like the chaining. Okay, it will not be covered by the midterm. But I just want you guys to be aware. Okay, what are my announcements? First, homework 3 will be uploaded today, and the sample midterm will also be uploaded. Okay. Second, okay, the midterm is 2 weeks from today, and the programming exam is going to be, I believe, is the third Tuesday. Okay, third coming Tuesday. Okay, so you need to take note on those things. Okay, and what else? Yeah, I think that's pretty much about it. Yeah. Oh, remember to register the Don't Judge. Okay, Don't Judge account. Okay, that's also important because you need that in order to take the programming exam. Okay. Any question for today? If no question, I will see you, the week after next, because next week there will be no class because of a spring break. Okay, have a good spring break. Okay, yeah, but don't forget to study because there will be a midterm right after the spring break. Okay, yeah, see you the week after next.